So I'll do a quick introduction, but let's wait a few more minutes before we get started. Victor, you might want to start sharing your screen actually, so that it's up there, just to test that it works.
Here, you see the slides?
Yeah, it works.
All right, great. Do you want me to leave it like this?
I'm sorry?
Do you want me to leave it like this, or do you want to switch back to the...
Sorry?
Do you want me to leave my screen share, or do you want to...
Yeah, you can leave it shared.
Okay.
I mean, my introduction will be pretty short. So.
All right.
Who is there somebody that takes attendance at all? We should probably have one of the graduate students to do that, because I don't see many graduate students that should be here.
Got it.
Gianluca, I mean, whoever is hosting the Zoom meeting, you can go to the Zoom webpage and find the attendance from there.
Ah, okay, very good. So that's Tierney. Perfect. That's the right
Great.
person. Yeah, fantastic. Thank you, Victor.
I did not know that actually.
No, me neither. Me neither. Yeah.
It's good to know. There is record for every student in attendance. We know who's here.
I was just going to take a snapshot, but that's my fault. That's great. So I guess we can slowly get started. Thanks for coming to our second SPRI seminar of this quarter. I'm Sinan Ketan, and me and Professor Shay Balogun are hosting this series for this quarter. And as I mentioned in the first seminar, in case you missed it, we're trying to organize these seminars in a way that they are thematically related to each other. So all of the talks in the fall quarter are mostly related to soft materials, active materials, and topics revolving around this. And today it's a great pleasure to have Professor Victor Lefevre to give our seminar. And he's a faculty member at Northwestern University in mechanical engineering. And he is going to talk a little bit about his work that's mostly focused on electroactive and magnetoactive materials. Just to give a little bit of background, Victor joined Northwestern a few years ago in 2018 as a faculty member. And prior to that, he received his PhD degree from University of Illinois at Urbana-Champaign in 2017. Right after that, he did a very prestigious postdoctoral fellowship at Brown. This is called the Hibbett Engineering Postdoctoral Fellowship. And he was there for a year working with a number of different people who are very well known in the mechanics field during that period. And after that, he joined Northwestern, and his work already has been recognized by societies such as ASME. He received the prestigious Haythornthwaite research initiation grant shortly after joining Northwestern, and he's doing really fantastic work in this field. His research is generally in the field of mechanics of solids and structures, with an emphasis in the multi-physics behavior of emerging soft functional multifunctional materials. And it's a great pleasure to have him today. So thank you, Victor, for accepting our invitation, and we look forward to hearing your work.
All right, thank you very much, Sinan, for the very kind introduction. Thank you very much as well for the invitation. It's a great pleasure to be here and be able to present my work in this SPRI seminar series. So the goal of the presentation today is twofold, really. First, to give you an overview of the methods that we use when we develop conceived models for these materials, and also give you an idea of what we've been able to learn about two different classes of these emerging soft multifunctional materials, namely electroactive and magnetoactive materials. So first, I'm going to talk about these materials. There's been a lot of interest over the past couple of decades now on highly deformable, soft, smart materials. And so I'm just going to give one potential application. There are many out there. So one application is soft robots. So I'm going to play the video in a second. So this is a small fish robot. The piece of soft active material is here. And you can actually see that you have this electrical wire that brings the voltage to the material, and that's what actuates it. And so the main idea between these materials is essentially controlling how they deform using here an electric field. So let me play the movie. So you bring a voltage through the wire, it deforms the material, and you see that that makes the fish swim in the tank. That's just one potential application, and people have been really interested in these materials, and in particular in making composites of these materials, where you would have a soft elastomeric matrix filled with a rigid semiconducting or even conducting rigid inclusions. So this is a schematic of a typical setup that people use to probe the mechanics and the electric specific behavior of these materials. So they take a thin film of the material, being either an elastomer or a composite, and they apply a voltage through the thickness of the film, and they measure how much the film deforms. And this deformation, this strain, is the so-called electrostriction. So it's here on the y-axis, and it's plotted here as a function of the applied electric field. There are two sets of results here on this graph. The bottom results here are for a homogeneous unfilled polyurethane matrix elastomer. And the top result here is for a nano composite of this polymer with a 7% volume fraction of inclusion. That's just a snapshot of what the macrostructure looks like. And so you can see that for a given electric field, the nano composite deforms a lot more than the unfilled matrix. So the enhancement here is about a factor of 20, which has probed, as you can imagine, a lot of interest in these composites, both from the experimental communities and the more theoretical communities to model with these materials. But what remains unclear is really where the microscopic mechanisms at the very low length scales that are responsible for this drastic enhancement in the properties of these materials. And so I'll show you what our guess and good guess is for these macroscopic mechanism. The second class of materials I want to talk about are magnetoactive materials, in particular so-called magnetorheological elastomers. So before, we're trying to deform these materials using an electric field. This is kind of the analogous problem where now you want to use a magnetic field to deform these materials. Of course, you might guess that if you just put a piece of elastomer, like a rubber band, inside of a magnet, nothing's going to happen because the rubbers and polymers in general are not sensitive to magnetic fields. And so people had the idea to embed iron particles, which are magnetizable, in these soft polymers, so that now the composite itself becomes responsive to any applied magnetic field. And so indeed, when you take such a material that's called a magnetorheological elastomer, and you make a specimen out of it, you put in the magnet, turn the magnetic field on, and you can see some deformation there. Here as well, there's been a number of applications for these class of materials. Again, I'm just showing one here for small scale robotics. So that's a cool application. You can see this soft robot here. It's made out of an MRE. And the idea is that you could control the way it moves and deforms using an electromagnet, and it would be able to crawl inside a human body, for instance, move around and perform some medical tasks. And so one nice feature about these MREs is that you can use a magnetic field or an electromagnet to actuate them, and there's no tether. You remember from the fish example, there was this wire that needed to bring the voltage. here there's no such thing. There's a number of experimental challenges when you just want to probe the material response of these materials. I'll talk about these at the end of the presentation, as well as some modeling challenges that we're going to discuss. So these are the two classes of materials I'm going to talk about. First, so I'm going to set up the problem just for electroactive materials. I'm going to, as I mentioned, present the methods and the solutions that we were able to obtain for their conceived behavior. Then we'll look at comparisons with experiments, the set of experiments I showed you earlier. And then, so this first part really will be on electroactive materials, and then we'll reuse all this for magnetological elastomers. All right, so before getting into the details, I want to show here a couple of key points just for hyperelasticity, finite elasticity, for those of you that may not be familiar with these points. And the idea being that later on, we're going to talk about finite electroelasticity. So we'll bring on mechanics and electric fields. So I figured maybe better to start with just pure mechanics. So there are, I think, 4 key ingredients to any mechanics problem. The first one is kinematics, or strains and deformation. That's an experiment that I like to, or an experiment, a demonstration that I like to do in class when I talk about strains. So I take a balloon, I draw with a Sharpie 2 lines, and then I pull on it. And what I like is very visual. You can see the deformation of the lines. You can track the motion of the different points. And kinematics and strains are very visual, easy to visualize. So for finite elasticity, we use the deformation gradient F. If you're familiar with the linear elasticity, that would be the small strain tensor epsilon. The next key ingredient is forces, so stresses and balance laws. We're all familiar in an intuitive fashion with what a force is. It's a bit trickier to formalize. But eventually, you can define the Cauchy stress T or the first polar kickoff stress S. We like to use the first polar kickoff stress when dealing with finite deformations because it's defined with respect to the undeformed configuration that we know. So it's easier to deal with than with the Cauchy stress. So there are also a number of balance laws that we believe in and we need to satisfy. So balance of linear momentum, divergence of the stress is 0, and balance of angular momentum, which essentially means that the Cauchy stress needs to be symmetric. So the next part is to have a relation between these two first aspects, strains and stresses. And this is specific to every single material, and that's called constitutive behavior. In the context of finite elasticity, the constitutive behavior is given by a strain energy density W. And if you use the second law of thermodynamics, you can show that once you have W, you can compute the first polar kickoff stress S by taking simply the partial derivative of F respect to the partial derivative of W respect to F. So I give you a relation between the stresses, the first polar kickoff stress, and the strains, the deformation gradient. Example, the simplest of all for elastomers, incompressible Neo-Hookean model. That's W, you take the partial derivative, and you get the expression for S, here accounting for the incompressibility constraint. And then the last ingredient is the geometry that the material occupies. And in general, when we look at constitutive behaviors of material, that's what we're going to do, we look at very simple geometries, so nothing crazy in this part. All right, so that's just for pure mechanics, hyperelasticity. Now we're going to talk about finite electroelasticity. And so we're going to look at these dielectric elastomer composites, and we're going to describe them as a two-phase particulate material, where we have a matrix phase, that's the elastomer, occupies a continuous domain in the material, and it's filled with a distribution of particles. So when this material is subjected to forces or electric field, it's going to deform and polarize. And so for the kinematics, the two independent variables that we're going to use are the deformation gradient, F, as well as the Lagrangian electric field, E. For the conceived behavior, we're going to have total free energy functions, Wm for the matrix, Wp for the particles. So these are objective functions of F and objective and even functions of E. So it's an even relation with respect to the Lagrangian electric field. These are not piezoelectric materials. These are standard regular dielectric materials. And similar to what I just showed you for regular hyperelasticity, we can take these partial derivatives to write down expressions for the total first paraelectric of stress S, the Lagrangian electric displacement D. So here for this total stress, it's just to emphasize that we have two contributions there, one which is the pure mechanics stress, as well as a contribution coming from the fact that there are non-trivial electric fields in these materials. And that's the so-called Maxwell stress. So this is a Lagrangian formulation. We have at our disposal these equations to write down the Eulerian counterparts of these quantities. These Eulerian counterparts, they're defined with respect to the deformed configuration, and they might be easier to use when comparing with experimental data that's been measured on specimens. So now for the balance laws and Maxwell's equations, here we're going to stick to the context of electroelastostatics. And so we have these four governing equations. So again, that's balance of linear momentum, that's balance of angular momentum, Gauss law, and Faraday's law. So because I said that W as objective, balance of angular momentum is already satisfied, so we don't have to worry about it. And for Faraday's law, we just have to introduce a scalar electric potential phi so that it's satisfied. So we don't have to worry about that either. The two governing equations that we really need to concentrate on are balance of linear momentum and Gauss law. And so here again, we're assuming that there are no body forces, no magnetic fields, no currents, no space charges. And for the time being, we're not accounting for dissipative phenomena. So this is, if you will, a description of the problem at the length scale of the particles, the microscopic length scale. But what we're really interested in too is the macroscopic response of these composites. And it's defined when you have separation of length scale, statistical uniformity of the macrostructure, and when the material is subjected to these so-called affine boundary conditions. F bar and E bar are constant. F bar is a second order tensor, E bar is a vector. And these boundary conditions represent essentially what people want to do in an experiment when they're trying to extract material behavior. And this is because when you apply these boundary conditions, the deformation and the polarization in the specimen are uniform, and this irrespectively of the geometry of the specimen. So what you're going to measure on the boundary of the domain is going to be the same everywhere you measure it. And then you can relate what you measure and obtain the considered behavior for the material. So that's what we want to do here. It's not difficult to show that F bar and E bar that we prescribe are actually the volume averages of the local deformation gradient and the local electric field. And these are the macroscopic deformation gradient and electric field. So we can define the macroscopic total stress S bar and electric displacement D bar as the volume averages of their local counterparts. And this macroscopic response that we're after for these composites can be written in this way as these two partial derivatives of this quantity W bar that is solution of this variational problem here. So physically, what does this mean? These two partial derivatives, they look very similar to the ones I showed you earlier for the two behaviors of the matrix and the particles. And what they mean physically is that even though this is a heterogeneous material, a composite, it behaves as if it were a homogeneous elastic dielectric with a total strain energy function W bar. And so W bar is simply the total energy density that you need to provide to the system to deform it and to polarize it. So here I've introduced C, the volume fraction of particles. It's going to be important in a second. And just to make sure that we're not doing anything fancy when solving this variational problem, the two early Lagrange equations associated with this problem are nothing but balance of linear momentum and Gauss law, which are the two governing equations that eventually we need to satisfy in the material. So that's the problem that we want to solve. Once you know the W bar, you can use these partial derivatives and you have the conceived behavior of the composites. And so the name of the game is computing solutions for W bar for different families of composites, and that's what I'm going to show you. So before talking about the solutions, let's talk about the constituents. So for the matrix, we're going to take that it's a non-Gaussian elastomer with an apparent permittivity that may depend on the deformation. That corresponds to this choice of finite function Wm. There are two parts to this function. The first one is this function psi m of the first invariant that describes the elasticity of the elastomer. It could be any function of the first invariant. It could be Neo-Hookean, the Gent model, the Arrhidabus model. We're going to use this model here. And on the right, you have a comparison between the model and some experiments, uniaxial tension results. They were done for a typical dielectric elastomer. It's VHB 4910 from 3M. The second part of this total free energy is characterizing the dielectric behavior. And so here, this choice represents this type of model to account for the fact that the permittivity of the dielectric elastomers may depend on the stretch. So this is a comparison between the model and some experiments for this same dielectric elastomer. And it's not perfect, but gives a good idea of the trend of what people have observed experimentally. That's for the matrix. For the particles, they're going to be nonlinear with possibly saturation of their polarization. So the elasticity is simply Neo-Hookean. And then we have this function SP that you can use to describe any dielectric behavior for the particles, in particular saturation of the polarization of ceramics. And so that's a typical choice that we make to do that. And again, the agreement is not perfect, but it gives a good idea of what's going on. So what I'm going to show you is that this formula here for W bar is a good model for the isotropic, for the response, elastic dielectric response of isotropic incompressible dielectric elastomer composites that are comprised of these two different constituents. All right, so that's the problem that we have to solve. So now I'm going to show you the methods that we use to do that and the type of solutions that we obtained. So I'm going to start with a class of composites where essentially we put the matrix and the particles where we want, because we're doing theory, so we can do that. These are constructed using an iterative process. And so, as I mentioned, we put the particles and the matrix where we want, and we do that in such a way that W bars, so the macroscopic response of this synthetic macrostructure, is the viscosity solution of a Hamilton-Jacobi partial differential equation. So the PD is given here, H is the Hamiltonian, and you have an initial condition given at 1 here. I'm going to comment on that in a second. This type of PDs, it's very rare that they appear in mechanics, but they appear a lot in physics. So in physics, here you have X, Y, and Z, the space variables. And so this role is played here by the components of the macroscopic deformation gradient and electric field, F bar and E bar. And in physics, you would have T as well, the time variable, and this role is played here by the volume fraction of particles, C. And so the way to understand this initial condition is that you need to integrate in time or in volume fraction from the initial condition that's given at C equals 1, which corresponds to 100% volume fraction of particles. And so if you only have particles, obviously the behavior of the composite is the behavior of the particles. So you need to integrate in volume fraction from C equals 1 to any volume fraction base of interest, say 0.15 for 15% volume fraction. Couple of remarks. In this function nu, we can control the specifics of the macrostructure. In general, it's valid for any appropriate choices of behaviors for the matrix and the particles. And it's valid for arbitrarily large deformations and electric fields. It's a very general result and very general formulation. So we started by doing some work in the small deformation limit, working out analytical expressions for the effective properties. In this case, that's 3 tensors. I'm not going to go into the details. Just want to mention that there are nice connections between these results and famous fundamental results in the literature of composites with the Hash and Strickman results and results by Eshelby and Maxwell. So in finite deformations and finite electric fields, there's no way around it. The problem is nonlinear. It's a PDE, so you need a computer to solve the problem for you. And we devised a so-called WENO finite difference scheme to do that. So to show you the key ingredients in the scheme, I'm going to use this model PDE with only two space variables, x and y. So the idea is to discretize the space variable in a Cartesian grid and then compute approximation on the vertices of the Cartesian grid. So once you have the variables at the vertices, then you carry out the integration in time, in the fraction. That's the so-called method of lines. There's a lot of people that have worked on schemes for these type of problems, including famous mathematicians. And they came up with a number of rules that your choice of scheme needs to satisfy if you want to converge to the viscosity solution. So the rule is, for instance, that the numerical Hamiltonian, that's what you put in the computer, needs to be monotone and consistent. There are a number of there in the literature, so we used one of these. Then you need to evaluate the spatial partial derivatives with respect to the space variables. And so to do that, we used this so-called WENO, so weighted, essentially non-oscillatory finite difference scheme. So it's a kind of fancy finite difference scheme because it's fifth order accurate when the solution is smooth and remains third order accurate when you have discontinuities in the solution or in its gradient. And that's something that we may expect. That's typical for solutions of these PDEs. One thing that we have to do is to work out how to account for the fact that in our problem, there's no periodic boundary conditions. As far as we know, everything that's been done on these schemes, finite difference type of models were done for periodic domains, but that's not the case here. So we have to work out a way around that. And then finally, the last ingredients, it's a time integration. We used an explicit fifth order Runge-Kutta type of scheme. So we put everything in the computer. There's a lot of moving parts. So what we did was look at a special case of practical interest. I'm not going to go over the details. It's just you switch the electric field off, so just mechanics, and you look at composites where it's aligned cylindrical pores in the composite. So if you do that, the PDE is a bit simpler. There are only two space variables, the two principal stretches, on the one bar and on the two bar. And what's remarkable about this problem is that there exists an analytical solution. It's not every day that you encounter a nonlinear PDE and there's a physical meaning, and on top of that has an analytical solution to it. And so what's nice with this analytical solution is that we can do some convergence study to check that the scheme works properly. And this is just showing you that we have the rates of convergence that we were expecting. There's something in the chat. I'm gonna have a quick look at it. Oh, okay. All right, so what's nice about this formulation as well, I haven't mentioned yet, is that what you obtain is the macroscopic response, W bar, all at once. So for your computational domain, you obtain all the response covered in this domain. That's a bit different from what I'm going to show you next. We're going to use finite element where you have to follow one loading path at a time. Here you get the entire free energy landscape. So that's what it looks like. So it's 15% porosity for this composite. As a function of the two principal stretches, lambda 1 bar, lambda 2 bar. And then you can follow any loading path that you want. So this is for uniaxial tension. You follow this line, you compute the partial derivatives, and you get the stress. So you see here different volume fractions and a very good agreement between the exact solution and the prediction from the scheme. That's another loading, for instance, transfer shear, and the same thing. You follow the path, compute the derivatives, and very good agreement there as well. All right, so now that we have confidence in the scheme, we use that for the problem where there's no analytical solution. So the response of these isotropic dielectric elastomer composites. And that's what the energy landscape looks like. Again, you follow one loading path or another, and you get the response that you're interested in. All right, so that's results for this first class of macrostructures, these iterative macrostructures. What I want to show you next is what we did for composites that are a bit more realistic, where now the particles are spherical in shape. So what we want to do is try to represent the isotropy, the overall isotropy of these composites that's observed experimentally. And there's a good way to do that computationally. The idea is to use periodic composites that are made out of the periodic repetition of a unit cell, cubic unit cell, where you have a random distribution of particles in the unit cell. And so even though these are periodic composites, their behavior is not exactly isotropic, but you can check a posteriori that it's actually very close to being isotropic. So of course that gives a lot of flexibility for the shape, orientation, and so on of the particles. So here I have two examples. On the top, we have 3 different families of spherical particles, 3 different sizes. And here on the bottom, all the particles are of the same size. And again, you could have particles that have shape, ellipsoids, and things like this. I'll show an example later. So again, in the small deformation limit, we're able to do some analytical work, obtaining expressions for the effective properties in terms of solutions of linear and uncoupled PDEs, which is quite remarkable because remember, the problem itself is nonlinear and coupled. Yet, when you look at small deformations, all you need to do is solve linear and uncoupled problems. That's quite remarkable. Again, to find deformations, electric fields, there's no way around it. You need the computer to do the heavy lifting for you. And so what we did was to implement a nonlinear and coupled hybrid finite element framework to do that. So what we did was to use partial Lagrange transforms to account for the fact that these are incompressible materials. So in doing so, we introduce another field, a pressure scalar field that's associated with the incompressibility constraint, in addition to the displacement field and the electric potential. And so then it's just a matter of using the finite element framework and to convert the system of Lagrange PDEs associated with this variational problem into systems of algebraic equations that the computer can solve for you. All right, so I want to tell you a bit more about the discretization that we used. So we want to discretize the displacement field, the electric potential, and the pressure field. It's well known that for incompressible materials, you need to be careful about the choice of discretization for the pressure and for the displacement field, if you want the scheme to converge to the exact solution. In particular, in the context of linear incompressible elasticity, there's the famous Leidzenskaya-Baburskaya-Predzi Imsut condition. That's for linear elasticity. And so what we did was to use an element essentially designed for Stokes flow. Stokes flow is analogous to linear incompressible elasticity. So we used that tetrahedral quadratic-like element and added an extra layer of degrees of freedom for the electric potential. Of course, this is the problem we want to solve are nonlinear, they're coupled, so there's no theorem that can guarantee that the construction here is going to work. So what we did was a convergence study. We looked at the famous problem, the radial expansion of a shell, which you can work out the analytical expression. And once you have the analytical expression, you can do a convergence study and check that you have the good convergence rates. So 3 for the errors in the L2 norm for the displacement and the potential, and 2 for the L2 norm of the error in the pressure. All right, so now that we have confidence in the numerics, we can use it again for the problems that we're interested in. And so again, we got a composite with the elastomer matrix, the particles. And we're going to apply the electric field as is done in experiments. And you can see that this compresses and you can measure how much it deforms for a given electric field. All right, so these are these 2 different families of numerical methods for 2 different families of composites. And prompted by these numerical solutions, we're able to work out a closed form variational solution for isotropic macrostructures. I'm not going to go over too much details of how we did that. I just want to give you an overview of the key features of the solution. So it's valid for any appropriate choice of non-Gaussian behavior for the matrix. That's the choice of function psi m, and any nonlinear dielectric behavior for the particles that's in the function sp. So in there we have these amplified measures of strains and electric field, script I1 and script I5. What's important really is that by construction, it's exact in the small deformation limit. That's the formula it reduces to. You can see here mu tilde is the macroscopic initial shear modulus, epsilon tilde is the macroscopic initial permittivity, and m tilde k is the macroscopic initial electrorestrictive coefficient. For finite deformations, finite electric fields, it's not an exact solution, but it's a very accurate and very good approximation. So these are comparisons between the finite element results and the model for spherical inclusions. And you can see here, so the model is in orange, and the numerics is in dashed blue line. And you can see here that there is a good agreement between the two as far as the macroscopic energy is concerned. Of course, what we're really interested into is the derivatives of the energy. So the stress and the electric displacement. And again, these are some comparisons between the model and the numerics. And since there are a very good agreement between the two. All right, so let me look at a more specific problem, the case of rigid spherical particles of a significant practical interest. So first, let's look at the simplest choices for the matrix. So it's going to be neo-Hookean, and for the particles, they're going to be linear ideal electrics. So these are the two choices for psi m and sp. And in this case, this complicated formula I showed you earlier reduces to this expression, which is fully explicit, which is very nice. And you can see in there that you have the shear modulus of the matrix that enters in the formula. You have the permittivity of the matrix. You have the electrorestrictive coefficient of the matrix. You also have the volume fraction of particles as expected, C that shows up here and there. And we also have the initial permittivity of the particles, epsilon T, epsilon P, that appear in the formula. So as expected, both the behavior and the two faces and the content appear in the formula, and this is specific to isotropic distribution of spherical particles. It's fully explicit. So now for a more general case of a non-Gaussian matrix, nonlinear particles, so arbitrary choices for psi m and sp. So we're able to work out approximations for these three coefficients that appear in the formula. These are specific to the case of rigid spherical particles. And when you put everything in there, again, it's much simpler than it looks like. It's fully explicit up to this one nonlinear algebraic equation that you need to solve on the loading path that you are following. But nonetheless, it's very easy to implement in finite element software, so you can use this model to look at boundary value problems for these dielectric elastomer composites. I mentioned earlier, it's valid for any isotropic microstructure away from percolation. I'm just showing an example here. You can see here on the schematic, the particles here are randomly oriented spherical particles. The aspect ratio is 1.4. Because they are randomly distributed and randomly oriented, the composite is isotropic. So we can use the formula. So we computed ahead of time all the parameters that come in the formula. And then this is a true comparison between the prediction of the model in orange and the numerics in blue. This is not a fit. It's a real prediction and comparison between these two sets of results. So good agreement between the two. All right, so we have the model, we have the solutions, we have a good idea of the behaviors of these materials. Now let's compare with some experiments and see how well these models work. So first we're going to look at the pure mechanics case. We're going to leave the electric field switched off and look at the case of field elastomers. So in this case, the solution reduces to this expression. Again, it's fully explicit. And once you know the behavior of the matrix psi m and the volume fraction of rigid particles, that's the behavior. And so there were recent comparisons with experiments. so what this team did was to look at 3 different elastomers, so 3 different elastic response. So these are these 3 curves. And the blue lines are the fit of this model to this uniaxial tensor data. And what they did was to take these 3 different elastomers and make composites with the same volume fraction, 10% of large spherical glass beads. And these are the results for the composites, the dark points. And you can see here the model in orange works very well, and also some numerics, the dashed red line. So there's a good agreement of the numerics, the model, and the experiments. That's nice. It's really remarkable that such a simple formula works that well for such a complicated problem. All right, so now let's go back to electroactive materials and composites. This is the same data as I showed you the very beginning of the talk. The white triangles, that's the data for the matrix, and the black triangles, that's the data for the composite. So what we did was to fit the behavior of the matrix to the data that we have for the matrix, and it's a reasonable fit. And then put it into the model and see how that compares with the experiments. And these are the 2 predictions that we obtain. The orange is the model, and the dashed blue line is the numerics. And as you can see, it's very far away from the experimental data for the composites. Again, these are the black triangles here. So we're a bit puzzled by this. We checked all the calculations many times, and eventually had to conclude that contrary to an earlier initial conjecture in the literature, an isotropic distribution, that is the small volume fraction of stiff high permittivity particles, doesn't lead to any significant electrorestriction enhancement in these composites. And so in particular, the fact that these models are so far away from the data led us to believe that we're missing a very important physical phenomenon in the way we describe these materials, these composites. In particular, we believe that we're missing interfacial phenomena. It's well known that for nano composites, you have these interfaces, regions at the boundary between the particles and the elastomer, where essentially the behavior of the elastomer can be very different from what it is away from the particle. And so here in particular, we believe that we're missing the presence of interfacial space charges that would enhance locally the polarization of the composite, and in turn enhance their electrorestrictive properties. So we did some analytical work to look at this. I'm not going to go to the details, but now we have a composite as well as distribution of space charges. I'm going to skip all the details, but we're able to come up with governing equations for the macroscopic response of these composites, now with space charges, small deformation limit. And what turns out is that these composites, they behave as regular elastic dielectrics. But now there's an important catch. The catch is that their permittivity, epsilon tilde, and electrorestrictive coefficients, these are the 2 quantities that we're really interested in. These quantities are directly related and quote-unquote proportional to the charge content in the composite. And so that's really nice, because now we looked at some results, again, for distribution of isotropic distribution of spherical particles in red, now with this interface region where we have space charges located in this region. That's the model for the distribution of the space charges. Say a few words about this in a second. And so in this table, we have a comparison between the behaviors of the composites, depending on whether they have space charges, so here on the right, and without space charges on the left. So for the permittivity, you see that if you have space charges, you enhance the permittivity by a factor of 3. The mechanics doesn't change, obviously. That's the shear modulus, bulk modulus, and the 2 electrorestrictive coefficients. The first one is enhanced by a factor of 13, and the other one is enhanced by a factor of 45. There's really a significant, even drastic impact of the presence of space charges on the macroscopic elastic dielectric response of these materials. So we also did some more calculations now with numerics. So playing a little bit with the numbers that enter in this model, so the radius of the particles, the thickness of the interface, and the charge content. And now with the charges, we are able to get results that are much closer to the experimental data. And again, without the charges, that's the model that we had, the dashed blue line. All right, so this suggests a very promising strategy to design deformable dielectric composites with really remarkable and exceptional properties, because you can, if you can control appropriately the distribution of space charges, you can obtain composites with unusually large electrostatic coefficient, as well as possibly metamaterial type properties. There's a catch about this. This we had to prescribe. This is purely phenomenological because nobody knows if there are space charges in the first place and how they localize and distribute themselves around the particles. That's something that we had to prescribe phenomenologically. So what we are looking to do now is to use instead a physics-based model for the presence and mobility of these charges at the continuum level. So using ideas that have been used before for deformable semiconductors, where now you are using physics to describe how the charges move around the material and how they distribute themselves. This is just a 1D preliminary result. And you can see that, again, once you have space charges, you have a significant enhancement in the electrostriction. It's a completely different problem. It's another set of equations to deal with. You have a lot of difficulties and challenges to deal with the numerics, because you have these very sharp layers where the space charges concentrate. It's a completely different problem, and that's what we're looking at. All right, so that was all for dielectric elastomer composites. I'm gonna switch now to magnetological elastomers, as I mentioned in the beginning. And again, this is just a reminder of what they are. They are composites, soft silicon matrix filled in general with iron particles. And you want to actuate these using a magnetic field. Fortunately, there exists an analogy between electroelastostatics and magnetoelastostatics. So essentially, in this context, you can replace the electric field by the magnetic field H. You can replace the electric displacement by the magnetic induction. And the equations that we had, so Faraday's law becomes Ampere's law, which has the analogous form. And Gauss' law becomes Gauss' law for magnetism. And so there's this famous quote from Feynman. He said that same equations have the same solutions. So since we've already solved this problem for electroactive materials, we can reuse our solutions for the magnetoelastic response of magnetological elastomers. And so we have these solutions readily available. It's just a matter of reinterpreting what the different variables mean. And so we're going to use that to look at these MREs. So again, that's a typical setup that people use to probe the response of MREs. They make a specimen, in this case, that's a sphere. They put in the magnet, electromagnet, they switch the current on, and they measure how much that deforms. There's an important catch with this setup. It's the fact that the whole thing happens in the air. And in the air, as you know, you can have magnetic fields. And so you need to account for the air and the magnetic fields that are in the air, where you're going to look at the response of these specimens. That's what we did. Numerically, this is just a big sphere of air surrounding our spherical specimen of the MRE. The problem is axis symmetric, and so for the MRE, we use the formulas that we have for the WR. The problem is axis symmetric, so we did axis symmetric type calculations. And what I'm going to show you are results for simulations. So the magnetic field here is applied at infinity from the specimen. I'm not showing the fields in the air, but they have been computed. The top video is going to be the deformation, the components of the deformation gradients in the direction of the applied magnetic fields in the horizontal direction. And below, that's the first component of the Eulerian magnetic field. So I'm going to play the movie. We're cranking up the magnetic field. And these are what these fields are in this context. And so this is plotted with respect to the undeformed configuration. So the sphere, it's a cross section of the sphere, so a circle. And you see that it deforms a little bit. That's the deformed configuration. There is an important thing to mention here. It's the fact that the fields in such an experimental setup are not uniform. And what this implies is that if you're going to put a strain gauge and measure strains on the surface of your specimen, if you're going to measure it around here, you're going to measure compression. And if you put it there, you're going to measure the tension. And at the core of the specimen, you have tension as well. So these fields are non-uniform, and that has a significant impact on how you need to interpret the data. It's not a simple way of extracting material behavior. You need to treat these problems as really structural problems and do this type of calculations to compare with the experimental data. The fact that the fields are non-uniform, actually that was shown by Brown in 1966. So he showed that in a paper that the fields cannot be uniform in such a setting. However, back in the day, didn't have access to all the tools and technology that we can use these days. So it's really the first time that we're showing solutions for these non-uniform fields, and showing that they are indeed very non-uniform. And it's a critical aspect to understanding experimental data for these materials. We can look at different geometries for the specimens, for instance, a cylinder. And again, you see that you have corner effects, you have fields are highly non-uniform. So again, you need to run such a type of calculations to understand the data. What you can also do is look at ferrofluid inclusions. That's something that we've proposed because these iron particles, yes, they make the material responsive to magnetic fields, but they're very stiff. So they increase the stiffness of the composite. With ferrofluids, because the ferrofluids are soft, you make the composite actually much softer, and you can see that you can induce much larger deformations when you have ferrofluid inclusions. This is something that we've proposed based on this theoretical modeling, has yet to be explored experimentally, but that's something we're excited about. And again, as I mentioned, you can see that the properties of the ferrofluid inclusions are much better in terms of the strain that you can induce in these materials. All right, so to wrap up, I've shown you these two solutions or three families of solutions that we obtained for dielectric elastomer composites. Two were numerics, the third one was analytical. And we use that to show the dominant effect of space charges in dielectric elastomer composites. And we use these solutions as well for the analogous problem of magnetological elastomers. And we showed that you will need to look at a structural problem when you're probing the response of this material experimentally. And we proposed that using ferrofluid inclusions instead of the stiff iron inclusions leads to MREs with superior magnetostructive capabilities. Just want to conclude by mentioning two things, or one thing, I guess. There's this idea, the forward type idea that when you model composites, you want to have an idea of the behavior of the constituents and the macrostructure. You put that in the model and it gives you the behavior of the composites. And essentially that's what we used here to propose new ideas for these materials. But you can also use these models in a kind of reverse way, where you can compare your results with experimental data. And if they don't agree, it means that you are missing something important. You can identify that phenomenon that's missing, as well as use the models to probe the specifics of these very complicated, very small scale phenomena that might be otherwise very difficult to probe experimentally. So it's good to keep in mind that when looking at these composites, there's really these forward and reverse ways of looking at things, and both of them have their benefits, and it can be very nice to do. So with that, I thank you for your attention, and I'll be happy to answer any questions that you may have.
Thank you very much, Victor, for a very nice presentation. We have time for some questions. I believe Professor Jim Hamilton had a question and he took the first position early on. So Jim, go ahead and please ask your question.
Thank you. Sorry, Victor, to interrupt you in the middle of your talk.
No worries.
And terrific talk, to really on interesting subject, really beautiful slides and a well-typed set of equations. I'm hoping that you can give us a workshop or a seminar at some point on how to do this. That would be beneficial not just to me, but for others as well. My question actually has to do with the something that sort of appeared as a footnote in your presentation almost, as you mentioned the linear case,
yes.
The linearized case as being, I mean, you mentioned it and then you moved on, and I was curious as to why. Basically, is it that the linearized case has been solved and it's relatively there's nothing new to harvest there? I imagine that's a pretty interesting field. That little subset is not a little subset. It's actually a fairly interesting subset. Or is it just that the finite deformations and the material that you presented are fundamentally more of interest because this has applications in soft robotics and other things? So basically, why was it just a footnote?
Yes, so it was an important footnote, but footnote nonetheless, because as you mentioned, these materials fundamentally are soft, highly deformable materials. And so what we really care about are conceived models that are valid for arbitrary large deformations and electric fields. But as I mentioned, that was an important footnote because these are the first step that we did after setting up the problem. Instead of going right there to the very difficult part, coupled nonlinear problems, we took a first step, linearized the problem, and we already got a lot of insight and ideas in how these materials behaves. But eventually, there was just one step to getting to these more general conceived behaviors that eventually are the ones that we need because these are soft materials.
Thank you.
Any other questions from the audience?
Yeah, I had a question, Sinan.
Okay, Shay, please go ahead.
Thanks, Victor, for the very excellent talk. I was curious, how do you account for the couplings? So the coupling between the stress fields and the dielectric properties. I might have missed that earlier in the talk.
So I'm going to go back to the slide where I talked about the behavior of the constituents. That's going to be easier. But essentially, it's built in, and that's what's nice about this framework is that the ideas are the same as for hyperelasticity, so just elasticity, but by extended, where is it? Here. All right, so that's for the matrix. And you can see here that, so without this second part, just this first part, that would be just the elasticity of the elastomer. So typical classical hyperelastic modeling for non-Gaussian elastomer. And so the idea here, and it's not ours, it goes back to 2004, Dorfman and Ogden, and even before actually, where the idea is to append to the elastic description of the properties these terms that depend both on the electric field and on the deformation gradients. So that's hidden in I4 and I5. And you can see that whether you're going to take the partial derivatives with respect to F, you're going to have a contribution from this term that has something with the electric field. And so that's going to give you the contribution to the stress coming from the fact that you have electric fields. That's the Maxwell stress. So that's how it enters. It's right from the very beginning, it's all integrated in there.
Thank you.
Other questions from the audience?
Sinan.
Hi, Dr. Lefevre. This is, sorry.
Okay. Sorry.
I just had a question on the applicability of the different numerical schemes. I mean, you mentioned both the finite difference method and the finite element method for solving various problems. Mm-hmm. For which types of problems each of those is most applicable to?
Yes. So I guess I can go back to this slide where the figures. So this first problem, this first method, the WENO finite difference scheme, that's very specific to this family of macrostructures. And these are not really realistic macrostructures. These are what we call synthetic macrostructures. So theoretically, we put the particles and the matrix where we want, and we do that in such a way that the macroscopic response is the solution of this PDE. So from a pure applicability point of view, maybe it's not the best, but it's still very nice to have ideas of the behavior of these materials. There aren't that many families of composites for which you can obtain either analytical or numerical solutions. It's always good to have these kind of as a backup and to see what the behavior look like. For more realistic macrostructure, I think that's the method of choice using the finite element method. There's a lot of versatility and flexibility. So you could have, as I mentioned, spherical particles, you could have ellipsoidal particles, but even better, you could look at a picture of the macrostructure of your specimen and construct unit cells that are very close to be representative to the actual macrostructure that you have in the experiments.
Got it. Thanks.
Other questions?
Very quick one. I was wondering if since the materials that you were describing are likely to be subjected to cycles of electrical fields and magnetic fields, if hysteresis, either in the mechanics, the multiphysical response, or both, can play a role. It was already a very rich problem, so it may not be the very first thing to address, but further down the line for durability issues, what are your thoughts?
No, yeah, it's a critical part of the modeling of the behavior of these materials, especially these elastomers. They're very soft, so they're viscoelastic. And you could also have dissipative phenomena coming from the elec-tric side of things. That's something that we are looking at. In the small deformation limit, it's easier to do. I think it's been done already. For finite deformation, finite electric fields, this is still a topic of research. For instance, even in the pure mechanical case, so no electric fields, we don't know how to come up from a bottom-up fashion come up with a macroscopic response of composites when they are viscoelastic. So finite viscoelasticity, we don't know how to come up with model. I mean, we can come up with phenomenological models, but these type of models, homogenization type of models, it's really hard to do, and people are working on that. But yeah, so then the next step will be to add electric fields to that. But yeah, definitely that's very important. That's going to be important in modeling accurately the time dependence of the behavior of these materials.
Thank you.
Victor, I have one quick question, more regarding, where do you see the future of your research going? You mentioned that, you can go now to more structural effects, as you showed in one of your last slides.
Yes.
So you can also go the other direction, where you can go to smaller scales and look at microstructure effects. What do you want to do next? What's the big challenge for you?
So yeah, it depends on the family of materials you're looking at. So I guess I can switch back here. So for these electroactive composites, as I mentioned, that was slightly later on. The next step, and it's really a big challenge, and the own problem of it, a problem of its own, is accounting for the proper physics for these space charges. I mentioned everything we've done so far. The description of the charges that was phenomenological, so this choice of function here. We want to do better than that and have equations for the motion of the charges in these materials to be given as physics principle, and then solve that and see if that makes sense and compares with the experiments. So with best means going to smaller length scales. So now looking at these space charges. So what I want to do is look at this from, I guess, at the beginning, a continuum framework. So everything is a continuum. We have continuous distribution of space charges, but I'm sure that eventually we'll need to look at molecular dynamics type of approach, get more molecular level type of calculation to get some insights on these problems. For the magnetological elastomers, there's no such thing, and it's more, as you said, structural behavior type of, accounting for the structural behavior when probing the material behavior of these materials. And so potentially developing for these MREs with these soft inclusions and looking at this type of problems.
Great.
So going the two directions in terms of length scales, just electroactive, small length scales, magnetoactive, larger length scales.
Yeah, it's a fascinating field, and seems like there's a career's worth of things you could do with this going in either direction. So
yes, there's many things that can be done either way, and that's very exciting. And so yeah, I'm looking forward to doing that.
Yes. Fantastic. Thank you again, Victor, for giving a wonderful seminar. And thank you everyone in the audience for listening in. We'll continue next week. And thanks again.